Again, welcome to the digital carrier modulation lecture 2. In the first lecture, we have seen very fundamentals are needed for the digital carrier modulation. That is, what is the digital signal? So, what are the data elements? What is the signal elements? What is the bit rate, baud rate, and bandwidth? So, this is what with the various examples. So, we have studied in the lecture 1. In the lecture 2, actual carrier modulation we are going to study. So, as previously have seen, so the modulating signal, this is nothing but a digital data, whereas the carrier signal is always analog. So, we are again the modulating, and this is a type of the modulating signal is transmitted in the digital carrier modulation. At the receiver side, again the demodulation, we require the local oscillator. So, the local oscillator frequency and phase must be synchronized with the carrier signal at the transmitter. Again, after the demodulator, we are demodulating, we are getting the digital data. So, this is a very briefly already we have studied in the lecture 1. So, now we are going to study the digital communication, or you can say simply digital radio. So, it is the elaboration version of the passband digital transmitter. So, more elaboration is being given here. So, the first step is the pre-coder, is nothing but input, it is a digital data, and then it is an analog carrier signal, it is a buffer amplifier and a modulator, and then band pass filter and power amplifier and transmitting. So, this is a transmission media, generally is affected by noise. At the receiver side, it is again the band pass filter, tuning, and then after the band pass filter required the pass band, then is the amplifier and then demodulator, and we are going to get the digital output. So, again part of this one, we want to recover the carrier and clock recover. Again, we are using another circuit here. So, you should understand the clock frequency, clock and carrier frequency must be synchronized with the transmitter clock and carrier frequency. So, this is very brief. So, little bit closer if you go the one by one. So, what is the function of the precoder? So, the precoder performs level conversion and then encodes the incoming data into a group of bits that modulate an analog carrier. As we know that one, the natural signals are analog signals. So, we are transmitting a digital signal. So, that the analog signal, natural signals we are converted to the digital format. Or if it is a directly digital data is available like for example, it is a computer directly digital signal, or it is a textual information encoding with encoding, and then after that encoding we are going to the digital format. So, somehow we are going to get the digital signal here. So, this is the function of the precoder. Okay. And then this pre-coded digital signal we are modulating with the analog carrier. So, here the analog carrier signal is a sinusoidal signal, which is a highly stabilized carrier signal will be generated, say for example using the crystal oscillators, and then it is the buffer amplifier and then modulator. So, the function of the buffer amplifier is already known, well known. It is a matching between the modulator and the analog. So, input impedance and output impedance is matching with the modulator and also analog carrier signal, and also buffer amplifier is amplifying, or it is the current signals are amplifying to reach this one, and another function here it is isolating between the modulator and the analog carrier. If any problem arises in the modulator or a short circuited, it is a protected the analog carrier system. So, this is the function of the buffer amplifier, and then after the modulator, so we are making the band pass filter for the required transmitted bandwidth, and then power amplifier, and then feeding to the transmitter media antenna. So, this antennas, it is a propagating signal through transmission media, so that generally it is affected by noise. Okay. So, the transmission media, if you observe here the transmission media, the transmission medium can be a metallic cable or optical fiber cable, atmosphere, or a combination of the two or more type of the transmission systems. So, at the receiver side, as already we known, the received signal is maybe a weak signal, so that it may be amplifying, and also a tuning process is being given here to tune for only required bandwidth of the signal and then amplify it. After that again a demodulator, and we are going to get the digital data output here. Okay. And then this is the band pass filter. After that one we are carrier and clock recovery. So what is the function of the carrier clock recovery? The clock and carrier recovery circuits recover the analog signal and the digital timing clock signals from the incoming modulated wave, since they are necessary to perform the demodulation process. So to get the actual digital signal, we require the it is a clock and carrier synchronization required along with the transmitted carrier and clock. So this is the function of the simplified digital radio. So now what are the type of the digital modulation techniques? So usually there are basically three type of modulation, what we are calling amplitude shift keying, frequency shift keying and phase shift keying. Combination of the amplitude shift keying and phase shift keying, we are going to study the quadrature amplitude modulation. So the amplitude shift key is resembling the in the analog communication is the amplitude modulation. Similarly, frequency shift keying resembling the frequency modulation in the analog. So phase shifting is resembling the phase modulation in the analog. Okay, so combination of the amplitude shift keying and the frequency shift keying, we are going to study the quadrature amplitude modulation. So one by one let us go study this one. So this is briefly outlined here. So this is the modulated signal in the digital format, carrier signal corresponding amplitude shift keying, phase shift keying and phase shift keying and frequency shift keying. So B stands for the binary. So now before actual going to the transmission, let us see fundamentals. So in digital communication literature, the usual practice is to assume that the carrier signal is the analog carrier sinusoidal signal, generally represented by a mathematical equation is the C of t is equal to AC cos 2 pi f c t, where AC we are calling the amplitude of the sinusoidal signal and Fc is nothing but a carrier frequency, has unit energy measured over a one symbol bit duration. So this is a sinusoidal signal and is the has unit energy measured over a one bit duration or symbol duration. So we are transmitting the analog source, it is a modulating source in the form of a digital, so that it is having the bit duration, one bit duration, how many carrier signals are transmitting. So this is what the data element, this is the signal element as we already studied. Okay. So already the power of the carrier signal, already you know the power of the sinusoidal signal is nothing but AC square by 2 RMS square value, whereas the energy per bit duration, so the signal is transmitting only for one bit duration, it is the bit duration is TB. So for this time period, what is the energy of the signal? So that the energy of the over the transmitted signal bit duration, this is the energy of the transmitted signal for bit duration can be represented by a power into time, so that is AC square by 2 into TB. Or you can represent the AC is nothing but in terms of a 2 EB by TB. That means the amplitude of the signal is representing in terms of the energy and bit duration in terms of. So that we can write the carrier signal is nothing but in terms of energy per bit and also bit duration. So that it is conveniently for understanding the digital carrier modulation, we are representing in terms of magnitudes like this. So root 2 by 2b cos 2 pi f c t generally is referred as an orthogonal function of the basis function for the sinusoidal signal. Now a quiz test. Consider a sinusoidal signal carrier having a unit amplitude. The frequency is not given. Find the power of the signal. Compute the energy of the signal for pulse duration of 1 millisecond. This is a quiz test. So the answers for this one is, so he has been given as a unit amplitude, so that AC square by 2, so that 1 square by 2 is nothing but a 0.25 watts. Whereas the energy watts per time, so for 1 bit duration, what is the energy? So that is the pulse duration is given as 1 millisecond. So that the power into time can represent as 0.5 millijoules. So the power is represented in terms of the watts, the energy is represented in terms of the joules. Now we are going for the basic of the digital carrier system is the binary amplitude shift keying. So the amplitude shift keying or binary amplitude shift keying was probably the first type of the digital modulation to be practically applied. In its simplest form, it has been used for the radio telegraphy transmission in Morse code in the earlier days. So in a BASK, that is the BASK, generally it is referred as a binary amplitude shift keying, is a sinusoidal signal carriage simply gated on or off by a bit sequence to be transmitted. As already earlier represented or discussed. So this is the carriage signal. It is a bit duration of the modulating signal. It is a digital format. So 1 bit duration, how many number of sinusoids are transmitted. So gate, it is on. When it is on, it is a signal is transmitted. Off, there is no carrier signal is transmitted. So this is what the meaning of simply gated on and off. When a signal is a bit period is a high level, then signal is transmitted. When bit period is a low level, signal is not transmitted. So that we are calling as a gated on and off. So block schematic of the binary amplitude shift keying is represented by simply a multiplier, like in a analog transmission of the amplitude modulation. So here the modulated signal is a digital format, carrier signal is an analog format, whereas the analog communication, the amplitude modulation is both are analog, either modulated signal or carrier signals are analog form. Whereas the digital communication, digital carrier communication, modulated signal is a digital format, whereas the carrier is an analog format. So that we are simply multiplying. When the signal is a high level, signal is transmitted, carrier signal is transmitted, otherwise signal is not transmitted. So that gate on or off. So it can be represented, the transmitted signal is S of t is nothing but M of t into C of t. So in a binary amplitude shift keying, the signal can be defined S of t is equal to AC M of t cos 2 pi f c t, where t is in between the duration of 0 to TB, bit duration only. So where AC is the constant amplitude, already we have seen, M of t is the digital information of a modulating signal, either M is the digital format, so that is the 1 or 0. So FC is the carrier frequency, TB is the bit duration. So that the transmitted signal S of t can be represented like this. So S1t is nothing but AC cos 2 pi fct, whereas in terms of AC is represented in terms of the energy and bit duration, can represent like this also. So it is valid only when the logic is 1, that is the bit duration is high. When bit duration is low, automatically there is no signal, so S2t is 0. So S1t and S2t, it is when signal is high, signal is transmitted. When signal is logic 0, the signal is not transmitted. So average energy per bit already we have studied earlier, it is the EB. So once again represented like this. So 1 0 1 0 0. So it is a modulating signal. This is the carrier signal, this is the binary amplitude shift keying signal. So when signal is high, it is transmitted, when signal is low, nothing signal is transmitted like this. So this is the modulated binary amplitude shift keying, or simply we are calling as on off keying also. So if we observe in the time domain and frequency domain representation of the binary amplitude shift keying, suppose this is the modulated signal, we are representing in terms of a binary data, high, low like this. So it's a Fourier transform can be represented like a sync pulse, a gate pulse can be represented as sync pulse. So that combination of this one. So this is what the frequency domain representation of the digital modulating signal. Similarly, carrier signal analog form, already we know that one is the two spikes in the Fourier transform at the f of c and the minus f of c. When we both are multiplying, it is a gated on and off, so that it is the what we are calling as a BASK signal. Correspondingly, the Fourier transform is like this. So convolution of these two signals, the time domain is a multiplication, whereas the convolution in the frequency domain, so that at the each spike the signal is shifted, actually the frequency shifted here. So at each spike the same signal is shifted here. Okay, so this is the frequency domain representation of the binary amplitude shift keying. So this is what the more closely represented like this. So this is the frequency domain representation of a amplitude shift keying. So as we have seen in the AM, the bandwidth is the USB and LSB. Difference between the USB and LSB are taken. Similarly here also the same kind of bandwidth we have taken here. So each pulse it is a 1/2B, and here also 1/2B, so that the difference between the highest and lowest you can represent it as a RB, it is a bit rate. So the bandwidth of the ASK is simply a bit rate. So usually the bandwidth can be defined in two ways in terms of the hertz. So it is refers to the range of frequencies in a composite signal or the range of frequencies that the channel can pass. The another way can be defined in terms of the bits per second. So refers to the speed of the bit transmission in a channel or a link. So often referred to as a capacity. Now let us see the briefly the ASK transmitter receiver. Up to now what we have studied is how an amplitude shift keying, that is a binary amplitude shift keying, is generated. It is simply nothing but a multiplication or product of the digital modulating signal and the analog carrying signal. That's what we have defined, and the frequency domain and time domain representation also we have defined, and also bandwidth. Now we will see the how an ASK transmitter and receiving systems. So this is a transmitting system, as you already have seen. It is a product modulator, and a receiving system. So again the same characteristic is the product modulator and then low pass filter. So that after that we are getting the comparator, we are using either bit 1 or bit on or off, bit 1 or bit 0. So this is the transmitting system, this is the receiving system. Similar to the analog communication what we have studied, it is the product modulator, the transmitter, receiver side also the same characteristic is multiplying and filtering, so that we are going to get the analog signal. Whereas in the digital systems, so since it is the modulating in the digital format, either zeros or ones, so that we have to use a comparator, a threshold level. If it is a threshold level crosses a higher level, it is a 1, otherwise 0. So this way we can generate the modulating signal. This is the estimation of the modulating signal. So advantage, disadvantage of the amplitude shift keying. So the advantage is simply, it is a simplicity, it's very simple. It's the simply product modulator, so simply product of the modulating digital signal and analog carrier signal. Whereas there are various disadvantages also is there. So ASK is very susceptible to noise. It is prone to the high noise. Okay, so noise ASK is very susceptible to noise interference. Noise usually only affect the amplitude. Therefore ASK is the modulating technique most affected by noise. So whereas the application here, ASK using the transmit of digital data over an optical fiber. So now let us see the bit rate, baud rate and bandwidth for the ASK. Say for example I have taken as a S1 digital data transmitted ASK signal. So for this signal, how to calculate the bit rate, bandwidth and baud rate. So as we know that one, the bit rate is the number of bits transmitted per second. Baud rate is the number of signal units transmitted per second. So baud rate usually less than or equal to bit rate. These are the defined earlier. In ASK, the bit rate equal to the minimum Nyquist rate bandwidth. So bandwidth can be represented by FB by N, where N is equal to 1, N is equal to 1 in the sense either bit 1 or 0, so that only one element. So that FB and also baud rate. So bandwidth, baud rate and bit all are equal in the ASK system. Suppose for this signal, you can observe here for 1 second, you can assume that until here 1 second, it is here already given 1 second. How many bits are there? 1, 1, 1, 1 and 1. So that the bit rate is 5, And also signal elements, only one signal element only there, so only 0 is 1 here, so that it is the baud rate also 5, and bandwidth is again it is a 5 hertz. Now quiz tests. Consider an ASK modulated signal shown below. Find the bit rate and baud rate. So the answer here it is. So bit rate reciprocal of the bit duration, so that 1 by 0.1 microsecond, so that it is nothing but a 10 megabits per second. Similarly, baud rate, again in the ASK for the signal elements is 1, that is a binary, it is a simply baud rate and bit rate are both are same, so that baud rate also 10 megabits per second. If you observe the bandwidth, it is nothing but a 10 megahertz. So this is a multi-array, M array. Say for example, this is a binary, whereas this is M is equal to 4, M array level. So M array level already we have observed in the CO2, we can observe in the 4 levels, either 1 1 0 0 like this. So that in the 4 level ASK, this is the can represent as the 0 0 0 1 1 0 and 1 1. So here there are different amplitude levels for the each level. So this is what we are calling M array ASK. Until this all we have studied as a binary ASK, binary in the sense either 1 or 0, only 2 levels are there, whereas here is the 4 levels, so that the amplitude levels also 4 for the different levels here, 1 1 0 0 1 1 like this. So let us see certain problems based on the ASK, bandwidth, baud rate and bit rate. Now let us see example 1. Find the minimum bandwidth required for ASK signal transmitted at 2000 bits per second. So here is the ASK signal transmitting at 2000 bits per second, that means it is the bit rate, given as the bit rate is the 2000 bits per second. So we require to find out the bandwidth. So the answer is like this. In ASK, the baud rate and bit rate are same, and also bandwidth also same, so that the baud rate is therefore the 2000 bits per second, whereas the bandwidth also same, equal to baud rate, so the 2000 hertz. And example 2, given a bandwidth of 5000 hertz for an ASK signal, what is the baud rate and bit rate? So now the bandwidth has been given for ASK signal, what is the baud rate and bit rate? So since he is not given as the binary or M array, so it is assumed to be the only binary. So with this binary ASK, we can observe here the ASK baud rate is the same as bandwidth, which is means the baud rate is 5000 bits per second. Similarly, bit rate also same. Now another third question, determine the baud and minimum bandwidth necessary to pass a 10 kilobits per second binary signal using amplitude shift keying. Again here also is not given either M array or binary array, so that you have to assume the binary signal only, so that for ASK it is n is equal to 1. The minimum bandwidth is simply 10 kilobits per second, so that it is a 10 kilohertz, and it is again the baud rate also same, 10 kilobits per second. Now again a quiz test. What is the bandwidth of ASK signal that has bit rate of 5 kilobits per second? So the answer is 5 kilobits per second. So bandwidth is nothing but a 5 kilohertz. So with this one, the lecture 2 is end.